hypothesis. So null hypothesis is what you assume is true, like a coin is a normal coin, and the alternative hypothesis might be that it's biased towards heads or something. The result of the experiment or the statistic that it's calculated is called the test statistic. So that might be the number of times it lands on heads, something like that. Okay, let's try it out. So, any idea about this one?
What does it mean, the test statistics?
So it's basically what we're looking at. In this case, it will be X, the number of times it lands on heads.
Okay.
So how about B?
No. So that it is biased.
Null hypothesis would be it's not biased.
Oh.
So H null is that. So what is the probability that a coin lands on heads?
50-50.
You've been doing this for so long and you still say something like 50-50. So let's say, so P equals 0.5, where P represents the probability of the coin landing on heads. And how about H1?
The alternate one.
Yeah.
That is biased.
And how would you describe that?
Like, if it had a higher chance than 0.5 to land on heads.
Yeah, how would you represent that mathematically?
Like 0.6.
Better than that.
I'm not sure.
P is greater than 0.5. 0.51, that would be more than it. Let's see. So A, the test statistic is X, the number of heads in 8 tosses. B, if the coin is unbiased, the probability of a coin landing heads is 0.5. So H null, P equals 0.5. And then the other one is H1, P is greater than 0.5. Yep. Any questions there?
No.
Okay. You have a thing called significance level. So we'll find the probability of something happening. Let's say getting like 19 heads, let's say 17 heads out of 20 when you flip a coin. The odds of that happening by chance might be something like 1 in 100, 1%. And so if they say there's a 5% or less significance, then we would say, yeah, it's biased because it's less than the significance level. So it's not the type of thing that would happen by chance very often. Okay, let us try this one.
Is it the 23 people?
A suitable test statistic, let's call it X, the number of people who say they'll be supporting the candidate. So the number of people out of 20 who say they will support the candidate. Okay. How about B?
So would you say like that the people will be biased?
So you have to start with H null and then do H1.
So the first one is that they won't be biased and they just
It would have. So what's the probability they support her? If you ask a random person, probability they support her.
0.5.
Nope. In this case, it is 0.4. 40%.
Oh right, yeah.
And she thinks that they might be overestimating their support. So if the alternative hypothesis is true, then they're overestimating her support. And so what would be the alternative hypothesis?
That less than that less than 0.4 people.
That the probability is less than 0.4.
Yeah.
Yeah, that it's less than 40% of people. And then how about C? Any idea about that one?
What does it mean? Like,
so you might not know it. It is. Let me just see. So did they say 3 people say that they do? You would have to find like the probability of 3 people out of 20 saying that they will support her. And if that probability is less than 5%, then that's very significant. That means she has less support. So I'm going to try that now. You still just have normal calculator, is it?
the one that's like FX991EX.
I said to your mum I can send you a graphical one and you can just send it back when you're finished with it if you want.
I don't know how to use it.
You don't know how to use it. Okay.
I've never seen one before.
Oh. Well, the offer stands anyway. Menu. Distribution. I think it's 7. Yeah. We are doing binomial. But 1 second. So this one, let's say, so we're checking if 3 people is a less than 5% chance of that happening. What if 0 people said that they support her? Would that be the null hypothesis or alternative?
Alternative.
Yes. And so we do 3 or less. So 3 or 2 or 1 or 0. What is the probability of those happening? And so we use binomial cumulative. So not probability distribution, but press down, binomial cumulative distribution. So we can get all of them in one go. We can get 3, 2, 1, and 0. And we choose variable.
Okay.
So what is X? What is N? What is P?
Is X 20? X is 3.
Yep. What is N?
N 0.4.
Nope.
I don't know.
20.
Why?
It's the number of people. So that's the total population.
Is P 0.4?
Yes. So X is how many, like for this particular one, the test statistic. N is the total population, total number of people. And then P is probability. And we press equals. What do we get?
like a really small number.
Is it this one?
Yeah.
What is that as a percentage, roughly?
0.2%.
You have to multiply by 100. So that's roughly 1.596%, something like that. Compare that to the significance level. And what is that? How does it compare to the significance level?
It's lower.
This is less than 5%. That means that this is a very rare event to happen by chance. It only happens by chance 1.5% of the time. So which hypothesis do we go with?
The alternative one.
Yes. So this is a very rare thing. So we say sufficient evidence to reject H null. Therefore, we accept H1, the alternative hypothesis. And that's because this rare event happens only 1 or 2% of the time. We wanted something that was that happened less than 5% of the time. It did, so it's very unlikely that this happened by chance. It seems that they have been overestimating her support. So in general, X is the number of people out of 20 who say they support her. Mm-hmm. So the null hypothesis is that the probability of someone saying that is 0.4. Alternative hypothesis is that she's overestimating it, and so it's less than 0.4 probability. Mm-hmm. X is binomially distributed, where n is 20 and p is 0.4. Put that in with an x of 3 and you get something that happens 1.596% of the time. That's less than the significance level, and therefore there's sufficient evidence to reject the null hypothesis. Therefore we accept the alternative hypothesis. Any questions about all that?
No.
I just want to see something. So if we change the x to 4, what is that as a percent?
How do I go back?
Press AC.
Yeah. 5.095%.
Yeah, so that's something like 5.1%. And so if they asked 4 people, if they asked 20 people and 4 said they'll support her,
yeah,
would you accept H null or H1?
H null.
And why is that?
Because then it's above the significance level.
Correct. Yeah, it's just above the significance level, and so you could be like 94% sure, but not 95% sure or less, and that's what they want. That's hypothesis testing. Let us now do some wacky stuff. Let's see this one. So what we found there at the end that I just kind of threw in was the critical region. For this one, the critical region is 3 or less. And so if they got 4 or more, then we go with H0. The critical region is the region where you would accept H1. So the critical region for this one is X is less than or equal to 3. And you don't have to say it's between 0 and 3. Kind of goes without saying that you're not going to get -1 people. So 3 or less is the critical region for this one.
Wait, so they don't tell you what the critical region is?
No. You have to find that out a lot of time. And let's see. So finding critical regions. My explanation is better. Oh yeah, and if they say part D, what was the actual significance level? In our case, the actual significance level would be 1.596%. So it's less than 5%, and the actual amount is 1.596%. Okay, how do we do this?
I'm not sure where to start.
Calculator is where you start. What is x? What is n? What is p? Or what do you know?
I think P is 0.35.
Yep.
And is X 5?
Why is that?
Because is 5%.
No. What is n?
Does it say how many there are?
Yep. So x is binomially distributed, and in general, that's how it's written.
Oh, so N is 6.
Yes. And so we have to find what x gives us a significance level
Oh,
of 5%.
so you just do like trial and error?
Yeah. I just want to see something for a second. I just don't think that's a good question to start with. Oh, none of these are easy, are they? Let me just see this one. Hang on. It reduces the likelihood of failure. I think this is a good one to start with. Nothing strange about it. Okay, let's do this one.
Okay. Is the first one 10?
First, what?
Like the tested statistic.
Nope. Test statistic, let's just call it x. And that would be, let's say, the number of times the component fails.
So 3.
Sure. Well, no. Just the number of, this is just in general. Let's say the
So
number.
for that question, you never use the numbers that they give you from the question.
Yes.
Okay.
And in this case, it would be out of 20. So it's like x is binomially distributed, np, but we're looking at for R1. Okay. And in fact, for R1, what is n? What is p?
Why do we need to do this now?
Why not? Because I think it's a good idea. That's why.
But do we need it for that question though?
Yes.
Oh. So.
Not for part A, but.
Oh yeah. Okay.
It's to
So
clarify your thinking for part A.
is X 6?
Don't worry about x.
Oh.
What is n? What is p?
Is N 6?
Where do you see 6?
Because it says 3 times out of every 10, and then he tests 20. So I just thought, that's 6.
You're still telling me what x is. What is n?
N. I'm not sure.
That one's the total That is 20.
So is P3.
P is probability.
0.3.
Yes. Okay. We'll do part B now.
For the null one, is that the probability is 0.3?
Yep.
And then the alternative, would that be that is bigger than 0.3?
And so what does this person believe? Designs and believes it reduces the likelihood of failure.
So the probability of failure is 0.3.
And after his improvements?
It should be less than 0.3.
Yes, so that's the alternative hypothesis. And okay, part C.
Not sure how to start this.
Well, your guess was that X was 6.
Yeah.
So that's kind of what you would expect. It'd be like 20, you'd get about 6. So you could put that into your calculator.
Try it with 6.
Yeah. So what is X? What is N? What is P?
X, we put 6.
Mm-hmm.
And then N is the same as the one that we wrote in A.
Mm-hmm.
So 20, and then P is 0.3.
Yep. So what do you get there?
Like 60%.
Okay, so that's like a very high chance that you got 6 by chance, and that it wasn't. There's nothing significant about it. So we were asked to find the critical region where you get 5%. That would only happen 5% or less of the time. And so, what could you try?
Wait, how do we know that we just worked out the 6% one?
So when we press enter, we get like 60.8%.
Yeah.
So that means 60.8% of the time, you will take 6 just by random chance.
Oh.
And so we
But we want to find 5.
Yeah, so we want to find how many you would have to take for it to be 5% or less chance of happening. So a very rare event.
So we just like try and error a different number for X?
Yeah, that's one way to do it.
So could we try like 10?
Okay.
And then we get higher, so if we try like 2.
Mm-hmm. And in fact, he was trying to reduce the number of failures.
Yeah. Then we get 3.5%.
Okay, that looks pretty good. So the probability that X is less than or equal to 2 is 3.5%. Is that definitely the correct answer?
That's what the calculator says. It's like 0.03548 block.
I believe you. Is that so? So is it 2 or less? We can say is definitely the most number of failures you can handle.
Yeah.
Try 3. So what if X was 3? Because this one might be like 4%, which is still less than 5%.
It's 10%.
Yes. So you do have to actually check that.
Okay.
You don't necessarily need to write it down, but you do need to check it. So this is the correct one. 3 or fewer has a 10% chance of happening randomly. We want it with a 5% or less chance of happening randomly, and so 3 would be too many, so it has to be 2 or fewer. And so what is the critical region?
0.35 to
Nope.
5.
Nope.
I'm not too sure.
X is less than or equal to 2.
Oh,
Part D.
is that what we just found?
Yeah. So what is it?
0.35.
Yes. And I'll just write it down as 3.5%. So we wanted 5% level of significance. We got it, but the actual one was 3.5%, because sometimes it could be 4.5 or 1.5 or 1.2 or something. 3.55. X is less than or equal to 2. So 2 or fewer is good. 3 or fewer, too big. So any questions about that stuff?
No.
Okay. Now you picked this topic. So now let me think. Trace the number, that's 5. Let me think of this. No, I'll come back to that in this half second. Okay. Yep, looks like we're going to the more challenging ones already. Not that challenging though. Or maybe I should. No, I shouldn't. No. Yes. Looks like it has to be this one. Let me think about this though. I think I skipped over. I'm sure I did. Did I not? Nope. This is the one. Nope, this is not the one. But it might have to be. Okay, let's do proven. Okay, yeah, let's try this one.
So the test statistic is X out of...
No numbers?
Oh.
Or, okay, I'll let you use one number.
X out of 36 seedlings that survive.
Yeah. So number of seedlings out of 36 that survive. Okay, how about B?
So we type in on our calculator, N is N36.
Yep.
And P is 0.1.
Which is, nope, never that. Never that one.
On average.
Yeah.
12.
And as a probability?
Oh, do you do 12 divided by 36?
Yep. And that's
Okay.
That's the same as a third.
And then do we just leave like x is 3 or something?
Yes, we would have to find the critical region for this one.
So when x is 3, I got 4.894.
Hold on. We forgot two things: null hypothesis and alternative hypothesis for part A.
Oh, the null hypothesis would be that 0.3.
Probability equals 0.3 recurring.
Yeah.
I'll just write it as a third.
Okay. And the alternate would be that more than 3. P is more than a third.
Yes. This greater than means we have to do 1 minus. So with the graphical calculator, you don't have to do that. But with this calculator only has one way, and it always does less than. So we basically have to find the 90% level of significance and use that in reverse.
How do we do that?
So just do the same thing like we always do.
So like trial and error until we get like around 90%.
Yeah, I like you can use an inverse binomial calculation, but I just find trial and error to be quicker and easier.
Okay, so wait, would we increase or increase?
Try different things.
So say if we put instead of 3, like 6 maybe.
So you're messing around with x for this one. So try different things for x.
When x is 6, I got 0.0215.
What's your? Oh, sorry, I'm the one who's wrong. 36 and 1/3. Okay, we want a 10% level of significance.
So
That's like a 2%.
But
what we really want is something like 90%.
So we should increase it.
Yeah.
Let's say like 12.
Okay.
And we get 0.577, so we need to go higher again. So if it's 15, then we get 0.89.
Okay. That's close.
And then should we try 16?
So that's very close.
And 16 is 0.94, so that's further away.
So let's see. So the probability that x, what the calculator is showing us, is less than or equal to. So the probability that x is less than or equal to 15 is 89%. We want, so if we did 1 minus the probability that x is less than or equal to 15, we would get 11%. Is that good enough?
What do you mean good enough?
For a 10% level of significance?
No.
So what would we use? Or what would we try next?
The alternate.
We try 16. So what is probability x is less than or equal to 16?
0.94. So 94%.
And so what is 1 minus that?
6.
6%. So that is it. So what is the critical region?
I'm not sure.
So you might think it's, so it's basically x is greater than 16.
Oh.
Or you could say x is greater than or equal to 17, whichever you prefer. So 16 or less gives us a 94% chance of happening. And so 17 or more will have a 6% chance of happening. If 16 or more would be 11%, that's not enough. So it has to be 17 or more.
Wait, so you know how before we got 11%?
Yeah.
That's not good enough because it's above 10.
Yep.
Okay.
So this one is greater than 10%. So that's not good enough. And so this one is less than 10%. And so that's good enough.
Yeah.
And the critical region is that. And part C.
So we use the x has to be bigger than or equal to 17.
Yep.
To show that. Why would it be incorrect? Why would you incorrect?
It's just a fancy way of saying what's the actual significance.
Oh. So when x is 17?
That's not a probability. That's the critical region. So the level of
0.094.
It is 1 minus that number.
1 minus, so 0.06.
Yeah, so it's basically 6%, or you would be more accurate than that. You would use the 3 significant figures. So they said 5.84%. So we needed anything 10% or less, and the actual amount was roughly 6%. And so that's the one. That's the actual significance for this one. So if it is greater than, we're going up the other end. So if you've done like normal distribution or any of the distributions, you've got the left side and the right side. For greater than, we're going up the right side. And so with this calculator, you just have to do 1 minus to get that. So if you're trying to find 10% level of significance, find 90% and do 1 minus. And because we do 1 minus, it's like 16 or less is that. And so when we do 1 minus, it's 17 or more. Any questions there?
Yeah, wait, I don't understand the last bit, how you said, so we get 16 and then it becomes 17.
It's because we have to do 1 minus. So if it's 16 or less is not the critical region, then 17 or more is the critical region, because 16 isn't included in it. 16 is included in the less than region. So the critical region starts from 17.
Okay.
Bingo. Okay, let's try this one.
You know how it says suggest a model?
Yep.
What does it mean?
It could be it could be distributed binomially, normally, uniformly.
What does uniformly mean?
All the probabilities are the same. So like rolling a dice, they're all 1/6. That's a uniform distribution.
Please can you move it down a tiny bit at the end? So, wait, what are the options for the model normally?
So normal distribution, you could use binomial, you could use uniform.
What does binomial actually mean?
Think of bicycle. It's got 2 possibilities, and so that's something that we'll come to later. But they would say, like, when do you use binomial? and it would be when there's two possible outcomes, fixed number of trials, and a fixed probability. So fixed
So
number
is
of...
this one normal?
So let's see, a restaurant owner notices that her customers typically choose lasagna a fifth of the time, and it will change the proportion of customers choosing lasagna. So either it's a fifth or it's not a fifth. Either, yeah. So if there's two possible outcomes, a fixed number of trials for n, a fixed probability. So it's not like a conditional probability, like then yeah, it's binomial. And so we would say x is binomially distributed. You could just say binomial distribution, or it always helps to lay it out like this. So what would this be? Oh, we can do that in part B, binomially distributed. And we need the null and alternative hypotheses.
Wait, so n is like the total?
Yep.
But we don't have any numbers.
We do. Hang on. I just realized something. I'll start with an easier example of that because that's actually a new thing. Yeah. So there is a different type. So these binomial distribution. I'll just do a sketch for a binomial distribution. Might look something like that. If it's less than, it's down this end. If it's greater than, it's down this end. There is such a thing as a two-tailed test, which is this one. So this is a less than, this is a greater than, but together they would just be not equal to. So if they say, you could have like this one, probability is 0.25. The alternative hypothesis is it's not 0.25, and so it could be in the lower tail or the upper tail. And the way you deal with that is you halve the level of significance and put that for each tail. So you just do the two separate things that we did separately and just put them together in one question.
But how do you do that if there's not any numbers to be working with?
So they've given it to us up here. So this one, x is binomially distributed, 40, 0.25. They've given us the alternative, the null and alternative hypotheses, and so let's try this one. So you want the critical regions for this one. So 1% at the bottom and 1% at the top. So let's try the left tail first.
Do you just divide?
What is n? What is p?
P is 0.25. And n is is it 40?
Yeah. And so we need to choose different x's until we find something that's less than, it would be 2%, but we're cutting it in half to 1% because we have the lower tail and upper tail for this one.
Oh yeah. So we want it to be close to 1%.
Yeah.
So if we do 3, x is 3. then we don't get a nice number.
That's not bad. It's definitely less than 1%.
Why has it got the minuses to the powers?
Because they know you did GCSE maths, and so they assume you remember standard form.
I don't like it though.
You cheeked this man. So try 4. What if x is 4?
0.016.
And so it's not that?
Because that's over 1. No.
Yep.
That would be 1.6.
Yes. So probably that x
More than 1.
is equal to 1.6%. Probability that x is less than or equal to 3 is, so that one was 3 zeros. Sorry. So 10 to the minus 3. So 3 zeros and then 4, 6, 9, 5, 6, 8. So let's say 470. 470. And don't forget your decimal point. So 10 to the minus 3, 3 zeros. And so what is this as a percent?
0.47%.
Yep. And so, what's critical region?
4. Bigger than 4.
Critical region is possible x values that will make you choose the alternative hypothesis. That will
Less than 4.
Yeah, less than 4. Let's say less than or equal to 3.
But we got 4 on the calculator. That was less than 1%. So what's wrong with it?
When x was 4, we got 1.6%, didn't we?
Oh.
So that was a bit
yeah.
too big.
Okay.
Yes, okay. So when x was 3, it was less than 1%, so that one works. Okay, same thing, upper tail.
So now we want it to be like 0.99.
Yes. So we have the upper tail 1%, and so to the left of that is 99%, and so that's the way we have to find it with this calculator.
Okay, so I did x equals 20, and it's 0.9998.
Okay. What else could you try to make sure that one's the right one?
21 or 19.
I'd go with 19.
Oops. 0.9994.
Is that more than 99%?
Yeah.
Yeah. So 20 is good. 19 is good. We need to know.
18 equals 0.998. So that's over 99% too. 17 is 0.995. 16 is 0.988. So is that good there?
That would be a bit. That would be like 98.8%. We need 99%. So, what values? What's the critical region? What's the upper critical region?
17.
Yes. So
because 16 doesn't work.
Yes. So the probability that x is greater than or equal to 16 was 98.8%. Oh, sorry. It would be 1 minus that. So it's like, let's say 1.2%. The probability that x is greater than or equal to 17 is 0.5% roughly. And so the critical region is, what is critical region? The upper critical region?
Smaller than or equal to, no, bigger than or equal to 17.
Yes, well done. So this one, you're just checking if it changed. And so if you got 3 or fewer, it changed, you'd go with H1. Or if you got 17 or more, you'd go with H1. Any questions there?
Yeah. I don't understand what you just said.
So there is less than a 1% chance that x is less than or equal to 3.
Yeah.
And less than a 1% chance that x is greater than or equal to 17. And so if this was the number of times the coin lands on heads or whatever out of 40 throws, it would have to be 3 or fewer to accept H1, or 17 or more to accept H1. So they said, if they said it lands on heads twice, you'd say, oh yeah, that's H1. If they said it lands on heads 21 times, you'd say, yep, that's H1. If they said it landed on heads 15 times, you'd say, no, that's H0.
Okay.
Tricky. Okay, let's try this one.
So would n be 20?
Yep.
And p 0.4, and we want it to be less, no, just near 5%.
Not quite. That would be if it was less than or greater than. What is this one?
What do you mean?
So this one doesn't say p is less than 0.4. It doesn't say p is greater than 0.4.
It can't be equal to 0.4.
Yes, so it could be both. So
Right.
so what would you do with that? I'll just be a sec, sorry. I'm just finished up with the students. I just want to sit on the couch.
Sure, thank you.
Sorry for that.
Do you just...
So what was the... So do you remember what you have to do if it's not equal to?
No.
You cut the 5% in half. And so it is 2.5% lower one, 2.5% upper one.
So for the lower one, you just try and find near 2.5%, and the upper one you... like 97.5.
Yep.
Okay, so we can just... n is 20 and p is 0.4, and then we just put in any random for x. So if x is 10, then we get 0.872, which is going to be bigger than 97.5. No, that's smaller. Then we can try like 15.
Okay.
It's too big. 13. It's 0.993. So that's too big. 12. You get 0.978. So that's too big.
Okay.
11. And we get 0.943.
Hang on. Okay. So let's see. So we wanted 12. So we want like 97.5%.
Yeah.
Or more. And so, what's our critical region for this one?
11.
11 or more?
Yeah.
11, if you did 1 minus this value, so I do it by doing 1 minus answer, and you get 0.0565, so that's bigger than 2.5%, so that wouldn't work. When you put in 12 and you get
And
this,
then it's bigger than 97.5%.
yeah, so that one is like a 2.1% chance. And so what's our critical region?
12 equal to or bigger than 12.
Yeah, x is greater than or equal to 12. Is that full marks?
No.
Go on.
And we need to find the lower end.
Yep.
So if x is 2, I don't know that number, x is 5, then we get 0.125, which is too small. Try x is 7, then we get 0.
Hold on. When x is 5, that's 12.5%. It's way too big.
Oh. 0. So x is 3. I got 0.015, which is too small. And 4 is 0.05.
Right, so 4 happens 5% at a time. 4 or less happens 5% at a time.
But we want 2.5%.
Yep.
But when x is 3, we get 1.5%.
Right. So what's our lower critical region?
Smaller than or equal to 4.
That happens, what, more than 5% at a time?
Yeah.
We
So
want
3.
we want something with a 2.5%, something that like quite rare, and so it would be 3. Yeah. So this one was 1.6% at the time. The other one was 12 or more. Was, hang on, 12. I think it would have to be 13 or more. Sorry, because we are doing, so 12 is included in that, so it's 13 or more. That one was, I'll have to do 1 minus that. That was 2.1%, I think. Yeah. So that is 2.1%. And so the actual significance, you would add those two together, and you get something like 3.7%. So, which is less than 5%. So x is less than or equal to 3, x is greater than or equal to 13, and 3.7%. Any questions there?
No.
Yeah, so you're the first student I'd have taught it to who didn't do it in school. Every other student who does it in school says, can we do this because I did it in school and I don't know how to do it. Anything in particular you want to do next time? We can do the second half of this, or we can do something different, or you can let me know.
I'll let you know if there's anything. If not, we'll just do this again.
Okay. Any questions for me in general?
No.
Well done, Keelan. You did great. I look forward to typing again next week.
Thank you. Have a nice week.
You too. Goodbye.